Hi all, my name is Katerina Galitskaya and I am a senior antenna engineer at Radientum. My today's topic is challenges and solutions in designing millimetric waves antennas. So first, a little overview of our design project. The goal was to create phase antenna array that works in a relatively wide band, has dual polarization, and good scanning potential. Of course, such design faced a lot of challenges. We had to come up with new approach for antenna structure and understand how to do measurements. That's why this presentation is divided by several parts to pay attention to the most important challenges and findings. And the very first topic here is, of course, antenna structure. As everyone knows, a lot of things should be taken into account when working with millimetric waves. For example, topologies that might have worked good on lower frequencies do not behave the same anymore on higher frequencies. Feed structure becomes much more challenging due to small wavelengths and dielectric behavior. Combining single elements into array is yet another task. Coupling between polarization and the coupling between elements start playing significant role. Simulation time increased dramatically. So one of our goals was to simplify model as well as to get as close as possible simulation to real-life measurement results. Now moving to antenna structure itself. So antenna element consists of two separate PCBs, edge soldered together in order to achieve end-fire radiation. Vertical PCB is dual polarized cavity antenna. Horizontal PCB is so-called main PCB, which feed structure and ICs might be placed. Edge plating solution allows to avoid excessive port thickness, which would lead to higher cost. We simulated this case for different main PCB sizes, and the conclusion was so that the antenna element is not affected by it and can be potentially used as a component. Edge plating connection is very convenient for these purposes, but brings some mismatching, which can be compensated by more advanced antenna feeding. After single element simulation, we move forward to array topology. Total height of array component is 5.85 millimeters, which makes whole structure more solid and stable, even with edge plating connection. Distance between elements was chosen as half wavelengths of the central frequency to allow scanning. A final simulation was done with two PCBs and connector. We decided not to implement power divider for array measurements rather than to measure each element separately and combine results on post-processing. This allows us to see how each antenna behaves in the array structure and measure its S parameters separately. Antenna array shows good stable gain over wide band in simulation. Optimal distance between elements result in correct radiation pattern, which with one main lobe and low level of side lobes. After simulation phase, we move to implementation, where we paid special attention to manufacturer requirements, tolerances, and connector simulations. So chosen dielectric for millimetric wave design turned out to be quite a challenge. We looked through tens of available materials, but major part of them was either expensive or had a long delivery time. In the end, we decided to go with Astra high frequency dielectric. It has low losses and behaves predictably on frequencies of interest. For tolerance analysis, we used information from our manufacturer, drill hole sizes, dielectric thicknesses, edge plating stabilities. All of that were taken into account in tolerance simulation. Connector was one of the most problematic part of our design process. And then the structure required small, reliable connectors that can be installed manually. We looked through several options, but none of them had proper model for electromagnetic simulation. So we had to recreate connector from its drawing. Mismatch compensation was also designed to connector board transition. As might be expected, that led to not so predictable result on the measurement state, but eventually we managed to stabilize the connector model. As part of prototype preparation task, we created several models that we were interested into. In the end, we had fully simulated models of 4-element array and dual polarized single antenna element. Now move forward to measurements. Measurements were done using millimetric wave, anechoic chamber, and high frequency VNA. For studying purposes, prototypes were assembled manually in our house laboratory. This is how our prototypes look like after assembling two PCBs together and attaching connectors. To get more predictable measurement results, we prepared several identical prototypes and measured them. Here we have a comparison of measurement and simulation of single element. Correlation is good from frequency point of view, but there is still obvious mismatch from behavior point of view. Our next step will be proceeding with factory assembling for all parts to avoid manual soldering. Here is gain picture. It looks quite close. Maximum level is almost the same in required band. Radiation patterns of single element show good coverage and beam width. Unfortunately, we don't have combined array result at the moment to compare them to simulation, but judging by single element behavior, correlation is pretty good. As proven by this presentation, millimetric wave antenna array design requires quite precise approach to it. There are very few, if any, opportunities to tune the antennas afterwards once they have been manufactured. So that's why simulation is very important for this type of designs. That's all from my side. Thank you very much. Now it's time for your questions.